let's go through one of these Ferris wheel problems. So you can pause and read the problem if you want, but we have a Ferris wheel and we are interested in finding out some information about it. So the first part of the question asks, how fast are the riders traveling in kilometers per hour? So the riders are traveling along the outside of this Ferris wheel. So this is an example of a linear velocity or linear speed. However, we only know the rotational speed at the moment because we know how long the rides take and how big the wheel is. So first thing to do is figure out your circumference of the wheel here. So it's a little hard to do line conversions here on the computer, but we'll do that first. So we know that the wheel is 60 meters tall and that the rides take 20 minutes. So we'll insert an equation. We'll make a fraction here. We'll just make this a little bit bigger so that we can see it. So the first thing is that we know because you want your final answer to be in miles per hour, meters per second, that kind of thing. Now kilometers per hour in this case, and we're in meters already. So we know that the 2 times pi times the radius, so 2 times, I'm just going to write pi, times the radius. Now the wheel is 60 meters tall, so it tells you that the top of the wheel is up here at 60. So because it's 2 meters from the ground, it means that the diameter is 58. So that means that the radius is 29. So 2 times pi times 29 meters is in 1 revolution of the wheel. Now, we typically set this up in this way because we want to eventually cancel out the units that we don't want anymore. So, for example, kilometers, right? 1,000 meters. Let's make this a fraction. If you're writing this out, it's obviously a little bit easier. But 1 kilometer is 1,000 meters. And so now our meters are canceled. I don't think I can do like a strike through in an equation, but now that our meters are canceled out, if maybe even a color would help show that these are, that's a highlighter, the color, you can't make a color either. So anyways, those meters are canceled out. So now we are in kilometers per revolution. So what I want now is to cancel out revolutions and get some sort of time here. So the rides take 20 minutes. So we know that means 1 revolution is going to be 20 minutes. So I can say 1 revolution is 20 minutes. I suppose I could have my multiplication symbol here. So at this point, my revolutions, if you think of this, you can cancel that out because again, we're multiplying here. So revolutions cancel, meters cancel, we're in kilometers per minute. Now I just want to be in kilometers per hour. So I'll set up one more conversion here. I know how to get from minutes to hours. So I can divide, let's say 60 minutes is 1 hour. Now again, if you track your units here, you have meters cancels, revolutions cancel, minutes cancel. So you're left with kilometers per hour. Now if you come over to your calculator and you multiply all the tops, so that's 2 times pi times 1 times 1, times 29, times 1 times 1 times 60, you get your numerator. And I'll divide by 1 times 1,000 times 20. And my answer should come out to, it looks like about half of a kilometer per hour, 0.55 kilometers per hour, which is pretty slow. I mean, you get a 20-minute ride along this thing. So that's how you can use a line conversion to find the answer for that part. Now I realize there can be a little bit of confusion. I actually pulled up the key to double check my work, and if you look at here, I had put in 30 for the radius. So I think that the wording here could be a little bit clearer because the wheel is 60 meters tall which I think if you read that out, the top height of that is 60. The bottom has this 2 meter from the ground distance. So in reality, this is really 58. So I think in a situation like this where it's maybe not that clear, you'd be fine either way. So the second part, what is the angular velocity of the wheel in revolutions per minute? So we actually have most of that information right here. If you look at this part of our equation, we have revolutions per minute. We actually don't need to cancel out revolutions. So we need to get our information here, and then instead of converting to hours, we are in minutes. Now here you're in, let's just double check this. So you're looking for your angular velocity in revolutions per minute. So let's just start over. It's going to be a little bit easier. So the first angular velocity information that we know is that the rides take 20 minutes. So you know that you're going 1 revolution in 20 minutes. So the angular velocity is just 1 over 20, or 0.05. I was overthinking that at the beginning for a second. So revolutions per minute, you know that there's 1 revolution every 20 minutes. There you go. So moving on, sketch a graph of the function that depicts the rider's height above the ground in time versus time in minutes. So it's a little hard to do on the computer, but I can at least show how I would model that equation and where I'm going to get those numbers from. So really I'm going to do part D here, write the cosine equation that models the path of the rider. And that'll help with that part. So first things first, I'm going to need to look at my graph settings because I know that I'm going to be looking at time, and it takes 20 minutes for just 1 revolution to happen. So I think I'm going to start my x-axis at something like -5, and just because I don't like to start right at 0, and instead of 20 minutes, 40 minutes would be 2 revolutions. Maybe I'll go up to 45, so I'll get a couple cycles, and we'll skip by every 5 minutes. Now my y-axis, obviously this isn't going to go below the ground, but I'm just going to put something like -2 because I like to see my axis. My maximum, again, the ride goes up to 60, so I'll just go to something like 70 so we can see the top. And my steps, maybe I'll set by 10. So that's how I would set this up. I can even label my x-axis with time in minutes, and my y-axis is my height in meters. So going from there, I know I'm going to start with a cosine graph, and obviously it's not going to look like that. So first thing that I usually do is I'll move up my midline. So I know that this graph should be in the middle of 2, which is the minimum, and 60, which is the maximum. Now you might even, sometimes it's helpful to just put in those y equals 2 and y equals 60 if you want to know that it's not going to go below 2 and it's not going to go above 60. So the middle of 2 and 60, if you average those two together, is going to be 31. So, and you can actually look to make sure that you did it right, y equals 31. So that is where you can find out where the middle of your graph is. Now you want to change the amplitude. So your amplitude of this graph is going to be how high it goes above and below the midline. And to go from 31 up until 60, it's going to have to be 29. So you can adjust that. Now, once you have your maximum and minimum, if you want to get rid of your guides, you can do that. If you don't want your midline there, you can hide that. But they're sometimes helpful to start. Now, you know that this person is not starting at 60. There's no way, right? So you have a couple ways to do this. You know that they're actually starting down here at the bottom. Now I have to adjust my period as well, but I'm going to also have to think about adjusting the starting point. So let's adjust the period first so that I'm not in units of pi. Now remember that your period, I'll come over here to my document, your period is equal to 2 pi divided by b. So if you know your period is 20 minutes, and that's equal to 2 pi divided by b, and you solve for b, you multiply b to both sides and then divide by 20, you end up with your b is 2 pi over 20, which is equal to pi over 10. So I'll come over here in front of my x, and I'll make that pi over, oh yikes, let's try, there we go. So that means that has to be pi over 10. Now, this is great because I can see that my period is 20, so I've got this set up correctly. The thing is, I'm not starting at the top of this Ferris wheel when I get in. I'm starting at the bottom. So you have two ways you can do this. I'll show you both ways. So I'm going to take this equation, copy and paste it, and we'll show two ways to do this. So I'm going to hide this second one for a minute. First thing is, I think the easier way, is just make it negative. You'll start down here at the bottom, 2 meters above the ground. You go up to the top halfway through your ride, and then all the way back down to the bottom at the end of your ride. Your other option is to shift the graph. So, if I bring this black graph back, it's shifted by a factor of 10 to the right. So one way that you can do that is you just do a phase shift, and you can shift your graph over 10 to the right. And actually, because 10 is exactly in the middle of the period, you could make this a plus, you could make this a minus, and it's going to give you the same thing in this case because 10 is exactly half. So either of these two are valid equations that you can use. So that satisfies our answer for part D here. So moving on, part E says to write a sine equation that models the path of the rider in part C. So let's just take this equation and change cosine to sine. Now you should know that cosine is just a shift of sine. So I'll actually get rid of the black one here. So if I look at these two, let's make this maybe green. So these are now shifted, but they're only off by 5, which is 1/4 of the period. Right? The difference between sine and cosine is that they are a 90-degree difference. So in this case, 1/4 of the period difference. So I need to move my green equation, which is this sine equation, to make it match the red one. And to do that, I have to move it to the left 5 units. So to do a phase shift to the left 5, I'm just going to go plus 5, and then I would get my answer here for my sine equation. So I've got my answer for part D, my -29 cosine pi over 10, x plus 31, and then part E, there's a sine equation that models the same thing. For F, it says, what percentage of the time will a rider be more than 40 meters above the ground? So, the vertical axis is where 40 is in terms of above the ground. So I want to know how much time this happens. So if you look at this, you really want to know what percent of the time are you way above 40 meters. So let's come up with some intervals. I'll take some notes here on that document so that I can show what's going on. So you're below 40 from 0 to what looks to be here about right about 6. It's like my intersection here. It's hard to tell because it's not exactly giving me that intersection, but we'll say that's about 6. If you were using a graphing calculator, you could actually find the intersection as well. So for the first one, I'll show you how to do it both ways. So if I come to my graphing calculator, first make sure you're in radian mode, which I am. So I'll put in my cosine equation, it's a little shorter, -29 cosine, and then I've got pi over 10, well, let's do this in parentheses, pi divided by 10, x, and then plus 31. Now I'll take my window and I'll make it match. So I said my window for x was -5 to 45 minutes with a scale of every 5 minutes. My y minimum, I think I put -2 to, I believe, 70, and my scale was 10. And we'll look at that graph. It should match up what I've got. Now I'll also put in y equals 40, and So now you're looking at the same graph on both my, my Desmos graph and my graphing calculator graph. And I realized that actually my sine equation was hidden a little bit by my graphing calculator, so sorry about that. If I just get rid of one of these, you should be able to see it now. So if you're looking for the intersection, you want to know the intersection. So it's going to ask you for two curves. So if I was looking for this point, you have to take your little cursor here and just get close. So that's my first curve. Now my second curve, yes, of course, is the red curve, but you want to make sure it knows where you would like the intersection. So I'll come over here and find that. My intersection is 6.004. So, so from 0 to 6, if I'm over in my Google Doc now, from 0 to 6, this is less than 40. And from 6 until my next intersection over here, which I'm going to say is just about 14, it is greater than 40. And then it will be below 40 all the way down until 20. And that's one revolution, right? So if I just do this in one revolution, I can repeat it for the rest of the time. So come back over to my Google Doc as I take these notes. And this would be, from 14 to 20. This is less than 40. So as a percent of the time, from 6 to 14 is 8 minutes of your ride. So for 8 minutes, you're above 40. Now 8 minutes out of the 20-minute ride is 40% of the time. So about 40% of the time, you should be above 40 meters, 40 meters above the ground. And so that's how you solve the last part there.